Good morning everyone. Today I will explain or discuss 10 equations from our lectures in quantitative methods. The first equation is the probability of A is greater than or equal to 0. This means the probability of any event A is always greater than or equal to 0. This means negative probabilities are not possible. Probability is a measure of likelihood. Something happening can have a less than 0 chance. The lowest is 0, which is impossible, and the highest is 1, which is for certain. For example, if you roll a die, let's say event A is rolling a 2. The probability A is equal to 1 over 6, which can be converted to 0.167. Then 167 is greater than or equal to 0. The next equation is the probability of omega is equal to 1. This means the sample space omega is the set of all possible outcomes. The probability of something from the sample space happening is always 1. Something must happen when you perform an experiment. That's why the total probability over all outcomes is 1. For example, if you flip a coin, the omega is equal to heads and tails. The probability of heads plus the probability of tails is equal to 50% plus 50%, or 0.5 plus 0.5. If I add them both, it will always equal to 1. If A intersection B is an empty set, then the probability of A union B is equal to the probability of A plus the probability of B. This means if A and B are mutually exclusive, This means if A and B are mutually exclusive or no overlap, the probability of either happening is the sum of their individual probabilities. No overlap means we aren't double counting anything. For example, rolling a die. Event A is rolling a 1, event B is rolling a 2. These are mutually exclusive, means that you can't roll both. The probability of A union B is equal to the probability of A plus the probability of B. If we substitute all, it equals to 1 over 6 plus 1 over 6. To sum it up, it equals to 2 over 6, or we can convert it to 1/3. Next on our list is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. This is the general addition rule. It corrects for double counting when A and B are not disjoint. If events overlap, their intersection gets counted twice, so we subtract it once. For example, let's say event A are students who play football, which is 50%. And event B are students who play basketball for 40%. And 20% of players play both. Let's convert all percentages into decimals. Now let's substitute all variables to the equation, which equals to the probability of A union B is equal to 0.5 plus 0.4 minus 0.2, which is equivalent to 0.7. So this means that 70 students plays either or both sports. Probability of A union B is less than or equal to the probability of A plus the probability of B. The probability of either A or B happening is at the most of the sum of both. This becomes strictly less than when there's overlap. Overlap reduces the total union probability compared to just adding them blindly. For example, the probability of A is equal to 0.6 and the probability of B is equal to 0.5. Then if probability of A union B is less than or equal to 0.6 plus 0.5 is equal to 1.1. But since probabilities can exceed 1, the actual probability of A union B is less than or equal to 1. Next is the probability of the empty set, or is equals to 0. The empty set represents an impossible event or no outcome. If something cannot possibly occur, it has 0 probability. For example, rolling a 7 on a standard 6-sided die. The possibility of rolling a 7 is equal to 0. Next is the probability of A complement is equal to 1 minus the probability of A. The probability that event A does not occur is 1 minus the probability that it does occur. Either A happens or it doesn't. No other options, so the total probability is 1. For example, the probability of rain today is equal to 0.3. Next is the probability of no rain is equal to 1 minus 0.3 is equal to 0.7. Next is the probability of A union B union C happening is equal to the probability of A plus the probability of B happening without A plus the probability of C happening without A or B. This approach adds 3 events by carefully excluding previous overlaps, avoiding overcounting by subtracting overlaps progressively. For example, let event A student studies math is equal to 40%, and event B student studies physics which is 30%, of which 10% overlap with math. Next is event C, which are student studies chemistry, which equals to 25%, of which 5% overlap with A or B. Then we substitute with the following variables, which in conclude to the probability of A union B union C is equal to 0.4 plus 0.3 minus 0.1 plus 0.25 minus 0.5, which equals to 0.4 plus 0.2 plus 0.2 is equal to 0.8. If event A is a subset of event B, then the probability of A is less than or equal to the probability of B. This means if every outcome in A is also in B, then the chance of A is no more than B. you're measuring a smaller or equal portion of the same space. For example, let event A, which is students scoring A+, which is equal to 10%, and let's say event B are students passing 80%. Since all A+ students pass, let A is a subset of B and 0.1 is greater than and 0.1 is less than or equal to 0.8. Next is the probability of the complementary A union B is equal to the probability of A complementary intersection B complementary. This means that the probability that neither A nor B occurs is the same as the intersection of their complements. If A and B don't happen, that means both not A and not B happen. For example, the probability of A is equal to 0.6 and the probability of B is equal to 0.4. Now, if the probability of A union B is equal to 0.8, then the probability of A union B complementary is equal to 1 minus 0.8 is equal to 0.2. This equals to the probability not A and the probability of not B.